Okay, this is OCR AS level physics, paper 2, depth in physics from 2020. Links to the paper and the mark scheme are in the description for you. State what is meant by longitudinal waves, nice easy start. Direction of oscillations is parallel to direction of energy transfer. I'd like to say direction of propagation, but they don't seem to like that these days. We have an oscilloscope, we've got a frequency of that. We have a time base, so every division is 0.5 milliseconds. And the Y gain is 1 millivolt. Okay, so we have an amplitude of 2 millivolts. So we're going to be asked to draw it. Fine, nice and easy. So if the frequency is that, then we need to find out the time period equals to 1 over the frequency. So there's 1 over 500. So it's going to be 2 thousandths, so 2 times 10 to the minus 3 seconds, or in other words 2 milliseconds. Therefore, that means a wave is going to be this long. So it's going to be this long and it's going to be too high. So therefore we can just go like this. Oh, I haven't done it very shiny. I need to be curvier at the top and the bottom. And I failed, but you get the idea. Following are possible wavelengths of electromagnetic waves. Select from the list typical wavelength of a microwave and an X-ray. Well, you should know that visible light is hundreds of nanometers, so this is a little bit on the short side. So that is probably something like UV, something like that. Bigger than that, like 2 micrometers, that's probably going to be your infrared. Therefore, we need to go even bigger. And the wavelength for microwaves is about 2 centimeters. They're pretty big. They're the longest EM waves that we have. They can be longer than that as well, but it's about a few centimeters usually. X-ray has to be shorter. So our options are, well, 2 micrometers, like we said, that's just shorter than visible. So the next smallest one is 200 picometers. So that seems like it's going to be more reasonable. State 2 other properties of transverse waves. Can be polarized if they're transverse. Longitudinal waves cannot. They can be diffracted. Yeah, I guess longitudinal waves can be as well, in a different way I'd argue, but I don't know. We could also say they travel in a vacuum as well. We could say they consist of an oscillating electric and magnetic field as well. We could say reflected, a bunch of other things we could say there. Question 2, we have refractive index, we have speed of light. Okay, so the frequency f of blue light in air is about that. Okay, so v is equal to f lambda. So therefore, if we're looking for f is equal to v over lambda. So that's 3 times 10 to the 8 divided by 4.69 times 10 to the minus 7. So I'm just going to pop the 7 on top there. So times by 7, that's the opposite. So therefore, this just ends up becoming times 10 to the 15. So it's going to be hopefully something like 0.6 if I do this. So just going to say 0.64. There we go, times 10 to the 15, which is the same thing as 6.4 times 10 to the 14 hertz. Complete the table by determining V and lambda for when it's in glass. Okay, nice and easy. Well, we know that this is just how much slower something travels in a medium compared to air. Therefore, we can say that refractive index is equal to speed in a vacuum or air divided by c in the medium. And so that we know that's going to give us a number greater than 1. Therefore, if we're looking for this, swap these two round. Therefore, c is going to be just equal to speed of light in air divided by 1.53. This should give us 1 point something at a guess. So I'm just going to do 3 divided by 1.53, and that gives us 1.96. We should go to the same number of sig fig, so 1.96 times 10 to the 8 meters per second. And we're looking for the wavelength as well. We know that frequency is constant when a wave refracts, and so therefore we can say that, let's put in orange instead, lambda is equal to v over f. So that's our speed, 1.96 times 10 to the 8 divided by our frequency that we got before. And that gives us 3.06 times 10 to the minus 7, which looks about right. Okay, determine angle P. This, of course, is an n of 1.53. This is an n of 1. So, determine angle P. I is 30 degrees, so let's crack out Snell's law. N1 sine theta 1 equals N2 sine theta 2. N2 is, well, this is N2, this is N1. So N2 is 1, so that just disappears. So therefore we can say 1.53 sine of 30 is equal to sine of, well, P in our case. Therefore, just doing the left-hand side first, make sure you're in degree mode as opposed to radians, of course. So I'm going to press equals, and then I'm going to do inverse sine of my answer. And I end up with 49.9, so I'm just going to say 50 degrees. Determine Q using information from the table in A. Oh, whoops, sorry. I messed up. P is the reflected angle, isn't it? So actually this is 50 degrees down here. Q equals 50 degrees. Of course, this angle here is just going to be 30 degrees, isn't it? What a weird question. Of course we know that. That's a year 7 question, that is. Angle I is increased from 30 to 60 degrees. Describe and explain how P and Q will change. P will increase, always equal to, was it I, of course, yeah, fine. Q will also increase to a maximum of 90 degrees because, of course, we're then heading into TIR territory when the light goes, say, along here, and then it goes along here. Past that point, no refraction will occur. At this point, I is equal to critical angle. Let's call that theta C, why not? If I is greater than theta C, no refraction occurs, all light reflected. And this, of course, is total internal reflection. Nice questions so far. It's replaced with red light. The dashed lines show the original path. What's it going to look like with the red light? I'm going to use orange instead. So of course it goes down here, same angle of incidence, but you should know that red refracts less than blue, or blue light reflects, or blue light refracts more than red. Red refracts less than blue. So therefore, it's going to be going along there instead, not quite the straight. It's not going to go straight, of course, it is going to refract, but not as much as the blue light. Question 3, springs, L0 of 2, blah, 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 blah. They're adding a mass, blah, 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 blah. Fine. Okay. We have error bars. Okay, we're going to draw a line of worst fit, methinks. Show the gradient of the straight line of best fit is about that. Well, we're going to get a big triangle. We can't use a small triangle. Go from a nice point to a nice point. There we go. At least half the height and width. So what's that over there? 0.25. The only funky units? Centimeters. Okay. And we're going from 0.5 to 3.5. So that's 3 centimeters. So 3 divided by 0.25. So, wait, what? Oh, it's the other way around. Sorry. Oh, it's got meters per kilogram. Ugh, gross. Okay, so the gradient is equal to 0.03 meters divided by 0.25. And so that's essentially the same thing as 0.03 times 4. And so, yes, that does give us 0.12 meters per kilogram. What a weird way of doing it. Okay, determine the value for K. Okay, so our equation is up there. Okay, so let's write that out again. X is equal to mg over k plus r. Of course, this is a straight line graph equation. It was y equals mx plus c. We don't really care about that and that, but x, of course, is our y, confusingly, but we don't care. What's on our x-axis? It's the mass. So therefore, the gradient m is equal to, there it is, g over k. Therefore, swapping these round, therefore k is equal to g over gradient. Actually, you could have figured this out just from the units, to be honest. If it's k, it's going to be newtons per meter. So that's going to be 9.81 divided by 0.12. And that gives us, appropriate number of sig figs. So we're going to 2 sig figs there, 2 sig figs there. So we're going to go to 2 sig figs. So I'm going to say 82. And the unit, of course, is going to be newtons per meter. Now, how do we know that's the case? Well, let's just check. The unit of G is newtons per kilogram. The unit of this we saw was meters per kilogram. So they cancel. So therefore we have meters on the bottom. So that ends up being times by meters to the -1 on top. B, draw a worst acceptable straight line. Of course, it needs to be the maximum or minimum gradient that passes through all of the error bars. So let's go for the highest possible gradient. So I think it is going to hit that bottom one there. It doesn't necessarily have to hit the bottom of the first error bar, but it so happens that that is the case here. There we go. And I'm going to say that that ends up being about 0.13 meters per kilogram. Determine the percentage uncertainty in K. Well, like we said, K is equal to G over the gradient. G, of course, doesn't have an uncertainty, so therefore percentage uncertainty in K is equal to the percentage uncertainty in the gradient, which of course is just going to be equal to the difference in my values. So 0.13 take away 0.12 divided by the original 0.12 times 100. And so that just ends up being 0.01 divided by 0.12 times 100, which ends up being 1 divided by 0.12. And that gives me, I think I can say 8.3%. Question 4, ball, horizontal surface is going to take this trajectory here. We know that. Describe with the aid of a suitable diagram to show how an experiment can be safely conducted and how the data can be analysed. Fantastic. Ugh, 6 markers, I hate them. So we need to measure, R. So I would say something like use contact paper or slow-mo camera with ruler on ground to obtain R. Use meter rule to measure from edge of, what is it? Yeah, whatever. Edge of, well, actually, that's a good point, actually, because, you know, we're not told what's here. So we're probably going to need a set square there, aren't we, and a ruler. Edge of bottom of surface or under surface. Can use another ruler with set square as 0 point. Okay, how are we going to get V? Well, measure V with light gates, 2 light gates. You don't want to use one because it's a sphere, hard to do with 1 light gate. Measure V with light gates close together near edge of table or edge of surface. You don't want it slowing down. Okay, and well, classically, we're going to repeat multiple times for each value of V. Although, are you going to get it the same every time? No, I'm going to say we can't do that. I mean, we could do. We could just say repeat multiple times, obtain R for each V. Okay, let's have a look at our equation. R is equal to, what was it? V root Q over G. We're looking for Q, therefore R squared is equal to V squared times Q over G. We're looking for Q, therefore Q is equal to G R squared over V squared. I guess there's no point doing that. We're just going to keep it as the square root, to be honest. So we can have a graph of R against V, and we should end up with a straight line through the origin. And so it's not a very straight line, but you get the idea. Get the gradient of that. Gradient is equal to R over V. Therefore, Q is equal to G times the gradient squared. Of course, if you had R squared and V squared on the graph, it would just be the gradient instead. Not too bad, just weird. I hate those kind of questions. 5, car is traveling at a constant speed. It brakes. Braking force F acting on the car is constant. The mass of the car is that. The reaction time is 0.75 seconds, so that's there. And we can see it's a constant speed up until that point, which makes sense. State the gradient of the graph when t equals 0. Well, again, we can just go from here to here. So that's going to be 15 divided by 0.75. Gradient is equal to 15 divided by 0.75. So I believe that's going to give us 20 meters per second. Fine, easy so far. Explain how you can deduce from the graph that the brakes are applied at time that. Again, like we said, constant gradient for 0.75 seconds. therefore constant speed. After gradient decreases, therefore car is decelerating. Oh, what a nice question so far. Draw a tangent to the graph where time is that. Okay, so 1.75, right at that point there. So get a ruler. I would literally turn your piece of paper so your ruler is horizontal, and then you can do that, and you can make sure that it is touching at that point. Mine isn't great, of course, I don't have a ruler. But there we go, you're just going to find the gradient, that's it. Nice. You know how to do that. Determine the braking force. This, well, use information. So we know that F is equal to MA, and that's equal to change in speed over the time taken. And so, well, our mass was, what was that, 950? Yep, 950 kilograms. I don't need the kilograms, you get the idea. Times by the change in speed. And so we're going from this point up to this point here. The change in speed was from 20 at that point, wasn't it? This is 20 here, meters per second. And then this we saw was about 12 meters per second. So the difference is 8 times by 8 divided by, and how long did that take? That was 0.75 there, going across to 1.75. Oh, so there we go. It was just 1 second. Nice. So just 950 times by 8. So what is that? That's 1900, 3800, 7600 newtons. E, describe and explain the variation of the displacement with time when the same driver applies the brakes in the same car when the initial speed of the car is 10 meters per second. So half the speed. So we know that the thinking or the reaction time is the same, but distance travelled in this time is halved, of course. Apart from that, what can we say? Are we really going to be finding out the distance? I mean, we could find out the distance there, but it's just going to be half the distance. So I'm not so sure about this question. So I'll tell you what, if V is divided by 2, then therefore EK is divided by 4, because EK is equal to half mv squared. EK is proportional to V squared. So if V halves, then EK is going to quarter. And so therefore, if braking force is the same, braking distance should be quartered. That makes sense, right? Oh, yeah, they've said that too. Yeah, there we go. Fine. I'd say those are the marks there. They say that you should sort of like give some numbers. And like one of those things is actually how far it goes. There's no way I'm counting squares. I'm not going to do that. You shouldn't be expected to count squares. It's ridiculous. Like it's not physics. It's busy work. Okay, we have a weight of that, length of that, diameter of that. Calculate density rho of the metal. Well, we know that weight is equal to mg. So therefore weight is equal to mass times velocity times g. Therefore density is equal to weight over vg. Therefore that's weight over, well, our volume is going to be the area times the length times g. Fine, let's do the long way around. So that's weight over pi d squared over 4 times by L times g. That 4 can end up on top. So therefore density is equal to 4 times 7 divided by pi times, what's that, 32 millimeters. So I'm just going to say 0.032 squared times by 0.1 meters, because that's 100 millimeters times 9.8. I'm just going to call that times by 0.98. And that gives me 8,881. So I'm going to say 8,900 if I'm going to be consistent with sig figs. And that's kilograms per meter cubed. Okay, tensions at an angle, fine. What are we being asked? Oh, great. So we're being told to draw this guaranteed. Determine the magnitude of TB, 1 centimeter, right. Okay, you'll find that this ends up being 2.2 centimeters. So essentially that just ends up being 4.4 newtons. Draw a triangle of forces to represent the forces acting on the cylinder. Determine the magnitude of TA. Of course, we know that we must have the weight pulling down. It's going to be 7 newtons. So 7 newtons is equal to 3.5 centimeters. So we're going to be going down to, so 1, 2, 3, down to there. That's our weight pulling downwards, and so therefore our third force, keeping it in equilibrium, is going to be our TA there. You should end up with something like 3.2 centimeters. So ultimately you're going to end up with, say, 6.4 newtons. Okay, determine the angle theta. I mean, you can use a protractor. I would, seeing that's a scale drawing, you end up with 39 degrees. Okay, next. Okay, we now have it just on a bench. Oh, it's going to be tipping. Calculate the minimum force of F to toppen the cylinder about X. So we're talking about this force, this moment, pushing it clockwise. And so therefore this weight is trying to keep it there by pulling anti-clockwise. So we know that one moment equals the other. So it's these two and then these two here, or rather half of that, isn't it? So therefore the moment due to F is equal to the moment due to the weight, and so that's going to be F times, well, actually we can just leave it as millimeters because it's just relative. So F times 100 is equal to 7 times, it's going to be half that, so that's just 16 mil there. So there we go. So just putting 100 over there instead, and we end up with 1.12 newtons. 2 sig figs, that's 1.1 newtons. Number 7, we have a power, we have a time. I'm just going to say 5 times 3,600. So that's going to give me 15,000, so that's going to be 18,000 seconds. We have a cross-sectional area, we have a current, whoopsie, can't be dealing with that, can I? And we have the, oh no, number density. What is the point in drift velocity? Urgh. Okay, calculate the resistance R of the heater. Power is equal to I squared R. Therefore, R is equal to P over I squared. So that's just as simple as 150 over 1.5 squared. And we end up with 66.66666. So it's just going to be 67 ohms. Calculate the number N of electrons passing through the heater in 5 hours. Okay, so we know that Q is equal to IT. So that's going to be our 1.5 times our 18,000. So that's just going to be 9. So that's going to be 27,000 coulombs of charge. Okay. Oh, fine. And we're looking for the number of electrons. Easy. And so therefore, number of electrons, not hashtag, that means a number, or used to anyway. Well, we know that we're going to take our 27,000 and we want a big number because, well, electrons are small, so divided by that. I mean, maybe it's worth making up your own units. I like doing that. So this is coulombs and this is coulombs per electron. So that cancels. And so we just end up with electrons on top. That works. We end up with 1.7 times 10 to the 23. Calculate the mean drift velocity. Yeah, here we go. So current is equal to A, E, N, V. Therefore, V is equal to I over all of this nonsense. And it is nonsense. So that's 1.5 divided by a cross-sectional area of 4.1 times 10 to the minus 9 times by, well, we know the charge of an electron is that, times by, what was our density? 7.9 times 10 to the 28. Okay, let's tidy up some powers of 10, methinks. Oh, hang on, this just ends up being 9, 19, 28. They all disappear. Isn't that cool? It's just 1.5 divided by all of those numbers. And we end up with 0.029 meters per second. Nice. Cost of 1 kilowatt hour is 16p. Calculate the cost of using the heater for 5 hours. So a couple of ways you can do this, but let's just do 5 hours times by the power. We've already got the power, which was, wait, what was it? 150 watts. So I'll tell you what, let's put it in kilowatt hours. So there's 0.15 kilowatt. And so that's it. If you just take your number of kilowatts and times it by that, you'll end up with that. So that gives us 0.75 kilowatt hours. Times that by 16p. It's just going to be 12p. Nice. Nichrome is a metal, silicon is a semiconductor. They have the number. I hate these questions. So silicon has smaller number density, and then resistivity silicon has larger resistivity. It's just 2 marks, so we don't have to explain it, which is nice. 8, electron diffraction, PD of that. Okay, describe and explain the pattern changes as the PD is increased. Include how the de Broglie wavelength is related to, okay. So we know that de Broglie wavelength is equal to h over p, or h over mv. However, if we're talking about accelerating electrons, we know that ev is equal to half mv squared. So we'll tell you what, we can just multiply both sides. We end up with mev equals that, or in other words, mev equals half of the momentum squared. So therefore momentum is equal to root 2 mev. We can say therefore lambda is equal to h over root 2 mev. Therefore, as m, e, h constant, lambda will be inversely proportional to the square of the PD. Therefore, e.g., if v is doubled, lambda goes down by a factor of root 2. Smaller wavelength results in smaller fringes, as well we're looking at here, and lambda equals d sine theta. Therefore, d sine theta. Therefore, lambda is proportional to sine theta. Oh, is that the end? There we go. Hope you found it helpful. If you did, please leave a like. If you really found it helpful, consider buying me a cup of tea by smashing that super thanks button. If you want to see the rest of the AS papers, then click on the card and it'll take you to the playlist. I'll see you next time.